Right, so be answering the tutorial sheet for mechanical properties of matter, which is your tutorial sheet 1 in semester 2, and it is very key, and you have to make sure that you understand everything that we are going to be doing here, and you are able to solve these questions on your own. So I'll guide you on how to handle this topic. All right, so let's start with the first question. The first question says a 200 centimeter long steel rod has a diameter of 20 centimeters. The rod is a part of vertical support that holds a heavy 550 kg platform that hangs attached to a rod's lower end. Ignoring the weight of the rod, what is the tensile stress in the rod and the elongation of the rod under the stress? Young's modulus for the steel is given as 2 times 10 to the power 11 pascals. Okay, so first thing first that we need to understand here, or to do before we do anything, is to correct data. So what data do we have? We have 1, the length, which is 200 centimeter. Number 2, we have the diameter. We need to correct that data. We have the mass. We need to correct that data. And then we have the Young's modulus. We need to correct that data. Number 2, there is a word which is very key and important that will help us find the answer to this question, which is saying that the rod is part of a vertical support. Okay, so which means, and another word which is going to help us to do the calculations is where they are saying that a heavy 550 kgs platform that hangs attached to the rod lower end. So 1, the mass is hanging. What do we know about it? If the mass is hanging, we can calculate its weight by saying that weight is equal to mass times gravity. Alright, which is okay. Now, this is how we're going to do our solution. So, one skill which is very important in physics is to be able to sketch the problem. So, this is a sketch of the problem that we've been given. We are told that a steel rod of 200 centimeters. So, we have to convert that 200 centimeters to meters. So, it will be 2 meters long. Alright. And then we are told that it has a diameter of we have been told that it has a diameter of 20 centimeters. Okay, again we have been told that there is mass of what? Of 550 kgs. So we have indicated that's the mass. It is hanging as we can see, and we already said that since we have mass and it is hanging, there is acceleration due to gravity. We can calculate the weight, and we were told that weight is equal to mass times gravity. Now, the question doesn't ask us to calculate weight. The question is asking us to calculate the tensile stress, and we know that stress is equal to force over area. Now, the question that we're going to ask ourselves is that what type of force do we have here for something that is hanging? So we have a tension force, okay, a stretching force, which is tension. So where there's force, we're going to put tension. Okay, now tension, how are we going to calculate tension? Tension will therefore be equal to mass times gravity, because the force that we have here now is tension force. So we are going to calculate that tension force as mass times gravity. So this is what we are going to do. We are going to say over area. And how do we calculate the area? We need to be able, first, we have been given diameter. Alright? So if we have been given diameter, it was there to help us find the what? The arrow. So that we can use the arrow to find the area. Okay. and the area was found to be 0.30 centimeter cubic. Now, that is centimeter cubic, but we want to deal with meters, so we can still actually convert it to meters. So if we're able to convert that to meters, what we're going to have is that we'll have our formula: stress is equal to tension over area, and our weight, which is our tension force, we will multiply it by 550 multiplied by 9.8, or simply multiplied by 10 as a value for gravity. It will give us 5,500 over the area, which is 0.30 times 10 to the power negative 4, which will give us the stress to be 550 over 3 multiplied by 10 to the power 8 Newton per meter. That will be our stress. We would have answered that question as required, but I added this solution down here to say, what if we were asked to calculate the strain from the same information? Okay, so if we were asked to calculate strain from the same information, given Young's modulus, we were going to say that, okay, we know that strain is equal to change in the shape over the initial change over the initial. And in this case, what are we going to have? If you want to calculate, if we're given Young's modulus, and then they ask us to say, okay, calculate the change in the what? In the length, the elasticity in length, which is Young's modulus we are given. Now, let's calculate the change in the length. I've added this part to just try and touch these two, the both forces that we have, which is strain and stress, so that we can explain all these things. All right, so we are from doing something that talks about stress. Now I added this part to talk about strain. So given Young's modulus, and we have been given the length of the material, now they ask us to calculate the change in the length. So we'll make what? We'll make our change in length subject to the formula, and therefore we'll have a strain over Young's modulus. Okay, so we have delta L over initial L, which is equal to S over Y, where Y is Young's modulus and AC is simply our stress. Okay, why are we having such a formula? Because we know that Young's modulus is equal to stress over strain. All right, so in a case where we're being given Young's modulus and we're just from calculating stress, and then we want to calculate strain, we're going to have a formula as in a strain equals to stress over strain, and then we'll have our value for strain to be, after doing the multiplication and the division here, we'll have the value for strain as 9.167 times 10 to the power negative 3. All right. Further, calculate the change in length. Okay. Another part, calculate the change in length. So to calculate the change in length, therefore, we're going to say delta L is equal to L multiplied by strain, which will be our L, we are given to be 2 meters. We converted the 200 centimeters to meters, which gave us 2 meters, multiplied by the strain, which we found it to be 9.167 times 10 to the power negative 3. So our change in L will be 18.33 millimeters, or 18.33 times 10 to the power negative 3 meters. So from question 1, I wanted us to tackle the two tensile forces, which is a strain and stress, and then try to manipulate the formulas maybe if they ask you to calculate the change in L, what you should do, to calculate the strain, what you should do, calculate the stress, what you should do. Alright, that is how we are going to handle question 1. So number 1 key is to understand, be able to interpret the information into what? Into a diagram, so that you can picture it and then come up with the equations and every necessary manipulation that you can do to the equation to calculate the requirement. Alright, let's go to the next question. Question 2. Question 2 is saying that a cleaning person tries to move a heavy old bookcase on a carpeted floor by pushing tangentially on the surface of the very top shelf. The bookcase is 180 centimeters tall and 90 centimeters wide, with the 30 centimeters deep shelf, all partially loaded with books. The total weight of the bookcase and the books is 600 Newton. If the person gives the top shelf a 50 Newton push that displaces the top shelf horizontally by 15 centimeters relative to the motionless bottom shelf, find the shear modulus of the bookcase. So now the question is, what is shear modulus? Alright, first thing first, what is the shear modulus? So, from question 1 we were talking about Young's modulus, which is elasticity in length. Now, shear modulus is simply elasticity in shape, and shear modulus is given as, let's say, shear modulus is given as shear stress over shear strain. And we know that stress is always given force over area. We also know that the strain is given as change in the shape over the initial. Alright, so let's see how we're going to handle this question. First, skill number 1, we need to be able to draw the statement, to picture, to make a free body diagram, and then from there we apply the equations that we know, and the data, using the data that we've been given, then we'll be able to find the required solution which they need. So this is how we're going to interpret this data. I want you to take a look at the diagram. So this is what we're actually talking about. This is all about the shear modulus. So when something is sheared, there will be some change which we will call delta x in the height. Alright, in the height, which we can refer as a small letter h as initial, or just a ref as L, but some may use small letter h. So now, shear stress or shear strain is given as change. Shear strain is given as change in x over initial L, or where you're using height, you have change in x over small letter h. Okay. Now, already said that shear modulus is given by shear stress over shear strain. Now, stress is given by force over area. Shear strain is given by delta x over L. So, we can simply try and make this formula more easy to use by saying that force over area divide by, those are high school mathematics, divide by delta x over L. Now, when we want to multiply, what will happen is that our force over area multiplied by delta x over, we will swap. The delta x will come down, the initial L will go as a numerator. So then we multiply. Force multiplied by initial L, it will be force initial L. And then area multiplied by delta x to be delta x. So the question is, what is the shear modulus? We're going to replace these values. Where there is the force, we were told that a person applied 50 Newton force. We put there. Where there is the initial length, we were told that the initial length was 180 centimeters. We put there. And where there is area, we were given the area there, that the area was 90. We were taught something about the area. Let me show you something. We were taught something about the area which we need to pay particular attention. We were told that the bookcase is 180 centimeter to and 90 centimeter width with the 4 30 centimeter deep shelves. So how many shelves do we have? There are 4. How many of there are 4 of what? 30 centimeter. So what we are going to say, I have 90 centimeter width and 4 30 centimeter shelves. So what we are going to say, we are going to multiply 90, which is the width, multiplied by the 4 30 centimeter. So we are going to just say 90 multiplied by 30 will get a 270 centimeter squared. So that will be our area. So the area that we have here is just L multiplied by B. Okay, that's our formula that we're going to use. So it will be 90 multiplied by 30, 270. Then we put where there is area as 270. And where there is delta X, we are going to put the change in X to be 15 centimeters. We're going to convert that 15 centimeters into actually meters. So once we do the computation, we will need to find the answer as 2.222 kilopascals. Okay, that's about the our shear modulus. That's our shear modulus. Okay. Question number 3. Question number 3 is saying that a hydraulic pressure contains a 0.25 meter cubic of oil. That is 1. We need to note that is the volume. Find the decrease in volume of oil when it is subjected to a pressure change of 1.6 times 10 to the power 7 pascals. The bulk modulus of oil is 5.0 times 10 to the power 9 pascals. Now, we need to understand, this question is coming from bulk modulus. Bulk modulus, which is elasticity in volume, and bulk modulus is given as negative. Okay, bulk modulus is given as volume stress over volume strain, and stress is always given as force over area. Strain is given a change in volume over the initial volume. But we always add a negative to this formula, because what we simply have to understand here is that there is for us to have to examine this property of volume stress over volume strain, which is bulk modulus. We are talking about a situation where we are squeezing a material, and when we squeeze a material, the pressure increases, but whereas the volume decreases. So in this case, what will happen is that if we would need to find the change in volume, then what will happen is that the final volume will be smaller as compared to the initial volume, and when we get the difference, our answer will be negative. So our formula tended to get to have a negative. All right. Now, F over A is simple pressure. Now, when you are squeezing this material, we are saying that there will be some change in pressure. The pressure will increase and the volume will reduce. So what the formula for bulk modulus therefore can be written as negative delta P, change in pressure, over the volume strain, which is delta V divided by initial volume. So now that we have that formula, we have the data that we've been given. Let's go ahead and apply that and be able to make delta V the subject of the formula. So let me just get to question number 3. Question number 3. So we're talking about bulk modulus being equal to stress over volume strain. Question number 3. So we're just going to say that we make delta V the subject of the formula, because I said earlier that delta P over delta V divided by V naught. So we are trying to get that formula and make delta V the subject of the formula. So if you make delta V the subject of the formula, we have negative delta V naught, or initial volume, multiplied by the change in pressure over bulk modulus. So where delta V is the change in volume, so we were told that the initial volume they gave us to be 0.25 multiplied by the change in pressure we were given, which was 1.6 times 10 to the power, and bulk modulus we were given as 5.0 times 10 to the power 9, and then on divide we are able to get a negative 8 times 10 to the power negative 24 meter cubic. Simple. Question number 4. The 4 tires of automobile are inflated to gauge pressure of 200 kilopascals. Each tire has an area of 0.0240 meters squared in contact with the ground. Determine the weight of automobile, and the answer we were given to say should be 1.92 times 10 to the power 4. But one thing you need to understand here is that what data do we have? Okay, we were told that there is a gauge pressure. We were also told that there is an area. Each tire would occupy that amount of area, and there are 4 of them. All right, and again, we are also aware that force, or we're also aware that pressure is equal to force over area. All right, pressure is equal to force over area. So in this case, if pressure is equal to force over area, we have been given area, we have been given pressure, we can actually first calculate force to be given as force over area. But now the question is, we have just been given the area of 1 tire. How are we going to get the area for the 4 tires, or the force for the 4 tires? So this is what we're going to do. Question number 4. Question number 4. This is what we are going to do. So question number 4, what we're going to do, we first find the force exerted by 1 tire. Since we are given pressure, and we know that the pressure is equal to force over area, so we can make force a subject to the formula to be that. So that was just the data. So force will be equal to area. For 1 tire, it was given as 0.0240. So we multiply. So which means 1 tire could exert a force of 4,800 newtons. So now we have 4 tires. What are we going to do? We are going to say, okay, if one can exert 4,800 out of 4, then we multiply 4 by 4,800 to have 19,200, which can be written as 1.9 times 10 to the power 4. Then we have answered question number 4. Simple. Question number 5 says, in hydraulic life, the force applied in a smaller cylinder of A1 is 3F1. In the area of the cylinder is 2A1. The maximum weight that can be lifted is, so you see here there's area 1 and area 2. And this we can get it from Pascal's principle, that the pressure applied at one point in the fluid, it is transferred and diminished to the all point of the fluid in the containing vessel. Okay, so that implies that from that statement we can derive to say that F1 over area 1 is equal to F2 over area 2. Right, so we're going to use that relationship to be able to come up with the answer to this question. So this is what we're going to do. Question number 5. Question number 5. This is actually what we are going to to do on question number 5. On question number 5. Question number 5. Okay. So, with question number 5, we're told that we're going to use the relationship from Pascal principle, that force exerted or applied, or force exerted on the fluid, it is applied in the fluid, is transferred and diminished across all points of the fluid in the containing vessel through to the walls of the containing vessel. So we have F1 over A1 is equal to F2 over A2. So what we're going to do, F1 is applied to the smaller cylinder, A1 we're talking about the smaller one, F2 bigger, A2 bigger is the area. So F1, we were told that it is equal to 3 times F1. So the force applied to the smaller cylinder is 3 times the maximum weight. We're told in the question. A2 will be equal to 2A1. The area of the larger cylinder is twice the area of the smaller cylinder. So what we're going to do, we're going to get the same equation and just substitute. Where there is F1, we're going to say 3F1 because they are said that it's 3 times. Where there is A1, we are going to need to say, okay, A1, 3F1 over A1, which is area 1, F2 over 2A1. And then we want to calculate the force 2 because we were told that we were told to calculate the force 2. And then we make F2 the subject of formula. We are just simply what we are simply doing here